right now. At this very moment, as you sit there watching this video, something absolutely wild might be happening all around you. You might be surrounded by 6 extra dimensions of space that are so tiny, so impossibly small, that no human eye, no microscope, no particle accelerator on Earth has ever been able to see them. And the strangest part is not that these dimensions might exist. The strangest part is that one of the most powerful mathematical frameworks in the history of physics actually demands that they exist, not suggests, not hints. Demands, the mathematics breaks down, becomes nonsensical, produces impossible answers if these extra dimensions are not there. The number is not 5 dimensions, not 7, not 12. The number is exactly 10. 3 dimensions of space that you can see and touch, 1 dimension of time that you experience every single second of your life, and 6 additional dimensions of space curled up into shapes so tiny that they are a billion times smaller than the smallest thing ever measured. This is not science fiction. This is string theory. And today, we are going to go deeper into this mystery than you have probably ever gone before. Let me ask you something before we begin. Have you ever wondered why the universe has 3 dimensions of space? Why not 2? Why not 4? Why not 17? You can move left and right. You can move forward and backward. You can move up and down. 3 directions. 3 dimensions. It seems obvious, right? It seems like that is just the way reality works. But here is the thing that keeps theoretical physicists awake at night. There is no fundamental law of physics that says the universe must have 3 dimensions of space. Newton's laws work perfectly fine in 4 spatial dimensions, or 5, or 50. The equations do not care. So why 3? Why do we find ourselves in a universe with exactly 3 large spatial dimensions? Is it a coincidence? Is it a fundamental feature of reality that we simply cannot explain? Or is there a deeper reason, hidden in the mathematics of the most fundamental theory we have ever constructed? Now let me throw some facts at you that are going to set the stage for everything we are going to discuss today. Fact number 1. The original version of string theory, called bosonic string theory, did not predict 10 dimensions. It predicted 26, 25 dimensions of space and 1 dimension of time, 26 total. That number dropped to 10 only when physicists added a concept called supersymmetry to the theory. Fact number 2. There are not 1 but 5 different versions of superstring theory. 5 separate mathematical frameworks, all requiring exactly 10 dimensions. And in 1995, a physicist named Edward Witten showed that all 5 of these theories are actually different perspectives on a single deeper theory that lives in 11 dimensions. 11. That theory is called M theory, and to this day, nobody has been able to write down its complete equations. Fact number 3. The 6 extra dimensions predicted by string theory are not empty. They are shaped into incredibly complex geometric objects called Calabi-Yau manifolds, and the shape of these hidden dimensions determines everything about the physics we observe. The masses of particles, the strengths of forces, the very fabric of reality as we know it. Fact number 4. The number of possible shapes for these extra dimensions is estimated to be around 10 to the power of 500. That is a 1 followed by 500 zeros. To give you some perspective, the total number of atoms in the entire observable universe is roughly 10 to the power of 80. So 10 to the 500 is not just a big number. It is incomprehensibly, absurdly, mind-breakingly large. And fact number 5. If even one of these extra dimensions were large instead of tiny, if it were stretched out like the 3 dimensions we can see, then gravity would behave differently, atoms would not form, chemistry would not work, and you would not be here to watch this video. So here is what we are going to do in today's video. We are going to start from the very beginning. We are going to understand what dimensions actually are, and I promise you, it is not what most people think. We are going to trace the history of how physics went from Newton's simple 3-dimensional universe to Einstein's 4-dimensional spacetime. We are going to discover how a little-known mathematician named Theodore Kaluza showed in 1921 that adding just one extra dimension to Einstein's equations magically produced electromagnetism out of pure geometry. We are going to build string theory from the ground up, understand what strings are, how they vibrate, and why they were proposed in the first place. And then we are going to arrive at the heart of this video. The mathematical proof. The actual reason why the equations of string theory demand exactly 10 dimensions and fall apart in any other number. We will explore what these extra dimensions look like, how they might be detected, and why some of the smartest people on the planet think they might be real, while others think the whole idea is an elaborate mathematical fantasy. This is going to be a long ride. This is going to be a deep ride. And if you are the kind of person who loves going deep into the mysteries of the universe, then you are in exactly the right place. So if you have not already, go ahead and subscribe to this channel and hit that bell icon, because we go this deep on every single video. Now let us begin at the very beginning. What is a dimension? Most people, when they hear the word dimension, immediately think of something mysterious. They think of parallel universes. They think of alternate realities. They think of that scene in a movie where someone opens a portal to another dimension and steps into a completely different world. But that is not what physicists mean when they talk about dimensions. Not at all. In physics, a dimension is something much simpler and much more precise. A dimension is a direction in which something can move. Or to be more technical about it, a dimension is an independent degree of freedom, an independent way that a system can change or vary. Let us start with the simplest possible example. Imagine a tiny ant walking along a perfectly straight wire. That ant can only move in 2 directions, forward along the wire or backward along the wire. That is it. The ant lives in a one-dimensional world. 1 dimension. 1 degree of freedom. 1 direction of possible movement. To describe where the ant is on the wire, you only need 1 number. You could say the ant is at position 7 on the wire. 1 number. 1 dimension. Now imagine that same ant walking on a perfectly flat tabletop. Now, the ant has more freedom. It can move forward and backward, but it can also move left and right. 2 independent directions of movement. 2 degrees of freedom. 2 dimensions. To describe where the ant is on the table, you need 2 numbers. You could say the ant is at position 3 in the left-right direction and position 7 in the forward-backward direction. 2 numbers. 2 dimensions. Now lift that ant off the table and let it fly through the air. Now it can move forward and backward, left and right, and up and down. 3 independent directions. 3 degrees of freedom. 3 dimensions. To describe where the ant is in the room, you need 3 numbers. Position in the left-right direction, position in the forward-backward direction, and position in the up-down direction. 3 numbers. 3 dimensions. This is the world we live in. Three spatial dimensions. Now here is where things get interesting. Is there a fourth direction? A direction that is perpendicular to all three spatial directions simultaneously? A direction that is not left-right, not forward-backward, not up-down, but something entirely different. Our brains cannot picture this. And that is perfectly fine. Our brains evolved to navigate a three-dimensional world. We evolved to dodge predators, find food, and build shelters in 3 dimensions. We never needed to visualize a fourth spatial direction, so our brains simply do not have the hardware for it. But here is the critical point. Mathematics does not have this limitation. Mathematics works perfectly well in 4 dimensions, 5 dimensions, 10 dimensions, 1,000 dimensions, even infinite dimensions. The equations do not care about the limitations of human visualization. And physics, at its deepest level, is written in the language of mathematics. So when a physical theory predicts extra dimensions, the question is not whether we can picture them. The question is whether the mathematics is correct and whether the predictions match reality. Let me give you an analogy that might help. In 1884, a school teacher named Edwin Abbott wrote a book called Flatland. It is a brilliant little story about a world that has only 2 dimensions. The characters in Flatland are flat geometric shapes. Squares, triangles, circles, all living on a perfectly flat plane. They can move left and right. They can move forward and backward. But they have no concept of up and down. The direction up does not exist in their world. Now imagine that you, a 3-dimensional being, decided to visit Flatland. What would the Flatlanders see? Suppose you are a sphere, and you slowly pass through their flat world. First, you touch the plane. The Flatlanders see a single point appear out of nowhere. Then, as you move through, the cross-section gets bigger. They see a circle that grows larger and larger. Then, as the widest part passes through, the circle starts shrinking. It gets smaller and smaller until it becomes a point again, and then vanishes completely. What would the Flatlanders think just happened? They would think they witnessed something magical, something inexplicable. An object that appeared from nothing, grew, shrank, and disappeared. But you, standing in 3 dimensions, would know there was nothing magical about it at all. It was just a sphere passing through a plane. Simple geometry. The Flatlanders could not understand it because they lacked the ability to perceive the 3rd dimension. Now extend this analogy one step further. What if a 4-dimensional sphere, a hypersphere, passed through our 3-dimensional world? We would see a sphere appear out of nowhere, grow in size, reach a maximum, then shrink and vanish. We would think it was magic. But a being who could perceive 4 spatial dimensions would see nothing unusual at all. Just a simple geometric object passing through a lower dimensional slice of reality. This analogy is incredibly important for understanding string theory's extra dimensions. We might be like the Flatlanders. We might be surrounded by extra dimensions that we simply cannot perceive because our senses and our instruments are confined to 3 spatial dimensions. The physics happening in those extra dimensions might be influencing our reality in ways we can detect but cannot directly see. Just like a Flatlander could detect the growing and shrinking circle without understanding the sphere that caused it. Now let me clear up some very common misconceptions about dimensions that I see everywhere on the internet. Misconception number 1 is that the 4th dimension is time. Well, sort of. In Einstein's theory of general relativity, time is indeed treated as a 4th dimension. Combined with the 3 spatial dimensions, to form what we call space-time. But time is fundamentally different from the spatial dimensions. You can walk left and then walk right and end up back where you started. You can move freely in any spatial direction, but you cannot walk backward in time. Time has a direction. It flows from past to future. Mathematically, this difference shows up in something called the signature of the metric. In the space-time interval equation, spatial dimensions get a plus sign and time gets a minus sign. So while it is technically correct to call time a dimension, it is a very different kind of dimension from the spatial ones. And when string theory predicts 10 dimensions, it means 9 dimensions of space and 1 dimension of time. The extra 6 are spatial dimensions, not extra time dimensions. Misconception number 2 is that extra dimensions are the same thing as parallel universes. They are not. A parallel universe, in the multiverse sense, would be a completely separate reality that exists alongside ours. An extra dimension is an additional direction within our own reality. These are completely different concepts. You can have extra dimensions without parallel universes, and you can have parallel universes without extra dimensions. Do not confuse the two. Misconception number 3 is that since we cannot visualize extra dimensions, they cannot exist. This is a deeply human bias, but it is not a valid argument against their existence. We cannot visualize an electron being in 2 places at the same time either, but quantum mechanics tells us it happens. And every piece of technology you use, from your phone to your computer, works because quantum mechanics is correct. We cannot visualize the curvature of 4-dimensional spacetime, but GPS satellites must account for it, or they would give you the wrong location by about 10 kilometers per day. Physics is full of things we cannot visualize, but that are absolutely real. Our inability to picture something says nothing about whether it exists. Now, let me take you a bit deeper into the mathematics of dimensions. One of the beautiful things about dimensions is that you can describe them using coordinates. In 1 dimension, you need 1 number to specify a location. In 2 dimensions, you need 2 numbers. In 3 dimensions, 3 numbers. We call these coordinates. In 3 dimensions, we usually call them X, Y, and Z. The key mathematical insight is that each new dimension adds a direction that is completely perpendicular to all previous directions. In 2 dimensions, the y-axis is perpendicular to the x-axis. In 3 dimensions, the z-axis is perpendicular to both x and y. In 4 dimensions, there would be a w-axis perpendicular to x, y, and z simultaneously. We cannot draw this, but mathematically, it works perfectly. The distance formula extends naturally. In 2 dimensions, the distance between 2 points is the square root of the change in x squared plus the change in y squared. In 3 dimensions, you add the change in z squared under the square root. In 4 dimensions, you add the change in w squared. In 10 dimensions, you add up 10 terms. The math is clean, consistent, and well-defined in any number of dimensions. There is a beautiful way to build higher dimensional objects that illustrates this. Take a point. 0 dimensions. Now drag that point in a straight line. You get a line segment. 1 dimension. Now take that line segment and drag it perpendicular to itself. You get a square. 2 dimensions. Take the square and drag it perpendicular to itself. You get a cube. 3 dimensions. Now take the cube and drag it perpendicular to all 3 existing directions. You get a 4-dimensional object called a hypercube or tesseract. You might have seen rotating tesseract animations online. Those are projections of a four-dimensional object into three-dimensional space. The same way a shadow is a projection of a three-dimensional object into two dimensions. A cube has 6 square faces. A tesseract has 8 cubic faces. And the pattern continues. In 5 dimensions, the equivalent object has 10 four-dimensional faces. The math works for any number of dimensions, and the patterns are elegant and consistent. But here is the point I really want you to take away from all of this. When physicists talk about 10 dimensions in string theory, they are not being poetic or metaphorical. They are saying that the mathematical equations that describe the fundamental strings require 10 independent coordinates. 10 independent directions in which the strings can vibrate. Not 9, not 11, 10. And if you use any other number, the equations produce mathematical nonsense. We will see exactly why later in this video. But first, we need to understand how physics got from Newton's three-dimensional world to Einstein's four-dimensional space-time. Because that story contains the seeds of everything that came after. For roughly 200 years, from the late 1600s to the late 1800s, the physics of Isaac Newton reigned supreme. Newton's universe was beautifully simple. Space was three-dimensional, absolute, and unchanging. It was like a giant empty stage on which the drama of physics played out. Objects moved through this stage according to Newton's laws of motion and his law of universal gravitation. Time in Newton's universe was completely separate from space. It ticked along at the same rate for everyone, everywhere, no matter what. Your clock and my clock, and the clock on a spaceship moving at 1,000,000 kilometers per hour would all tick at exactly the same rate. Space was space. Time was time. They were independent. They did not interact. They did not influence each other. And you know what? This worked. It worked incredibly well. Newton's laws predicted the motions of planets with extraordinary accuracy. They explained why apples fall from trees, why the moon orbits the earth, why tides rise and fall. For 2 centuries, every experiment anyone could devise confirmed Newton's picture of the universe. 3 dimensions of absolute space, 1 dimension of absolute time. Gravity as a force that pulled objects toward each other across the void. It was elegant, intuitive, and seemingly complete. But then, something happened. In 1865, a Scottish physicist named James Clerk Maxwell achieved something remarkable. He unified electricity and magnetism into a single theoretical framework. Maxwell's equations, as they came to be known, described how electric charges create electric fields, how moving charges create magnetic fields, how changing electric fields create magnetic fields, and vice versa, and how all of these fields work together. Maxwell's equations were beautiful. They were confirmed by experiment. And they contained a stunning prediction. When you combine the equations in the right way, they predict the existence of electromagnetic waves, waves of oscillating electric and magnetic fields that propagate through space. And when you calculate the speed of these waves, you get a very specific number, about 300,000 kilometers per second. The speed of light. This was a revelation. Light is an electromagnetic wave. Maxwell had unified not just electricity and magnetism, but optics too. 3 phenomena, 1 framework. Brilliant, but hidden within this triumph was a time bomb. Maxwell's equations predicted that electromagnetic waves, including light, travel at a fixed speed, about 300,000 kilometers per second. But speed relative to what? In Newton's universe, speed is always relative. If you are on a train moving at 100 kilometers per hour and you throw a ball forward at 50 kilometers per hour, someone standing on the ground sees the ball moving at 150 kilometers per hour. Speed adds up. It is always measured relative to some reference frame. So when Maxwell's equations said light travels at a fixed speed, the natural question was, fixed relative to what? The answer, physicists assumed, must be some kind of medium. Just like sound waves travel through air, light waves must travel through some invisible medium that fills all of space. They called this medium the luminiferous ether, and they set out to detect it. In 1887, two American physicists, Albert Michelson and Edward Morley, designed an incredibly clever experiment to measure Earth's motion through the ether. The Earth orbits the Sun at about 30 kilometers per second. As the Earth moves through the ether, there should be an ether wind, and the speed of light should be slightly different in the direction of Earth's motion compared to perpendicular to it. Michelson and Morley built an interferometer that could detect even tiny differences in the speed of light in different directions. They ran the experiment, and they found nothing. Absolutely nothing. The speed of light was exactly the same in every direction. There was no ether wind, no detectable motion through any medium. The speed of light appeared to be the same for all observers, regardless of their motion. This was baffling. It contradicted everything Newton's physics said about how speeds should add up. If you are moving toward a beam of light at half the speed of light, you would expect the light to appear to be coming at you at 1.5 times the speed of light. But Michelson and Morley's experiment showed that this does not happen. The light still comes at you at exactly the speed of light. No more, no less. This was a crisis. Either Newton was wrong about how speeds add up, or Maxwell was wrong about the speed of light being fixed. Both theories had been confirmed by mountains of experimental evidence. Something had to give. Enter Albert Einstein. In 1905, at the age of 26, working as a patent clerk in Bern, Switzerland, Einstein published a paper that would change our understanding of reality forever. His paper was titled On the Electrodynamics of Moving Bodies, and it introduced what we now call the special theory of relativity. Einstein's approach was radical in its simplicity. Instead of trying to explain away the Michelson-Morley result, he embraced it. He proposed two postulates. First, the laws of physics are the same in all inertial reference frames. There is no preferred state of rest. Second, the speed of light in vacuum is the same for all observers, regardless of the motion of the light source or the observer. That second postulate sounds innocent enough, but its consequences are utterly mind-bending. If the speed of light is the same for everyone, then something else has to give. And what gives is our everyday intuition about space and time. If I am standing still and I see you fly past me at 90% of the speed of light, I will observe something strange about your clocks and your rulers. Your clocks, as I observe them, will be ticking slower than mine. This is called time dilation. And your rulers, the ones measuring length in the direction of your motion, will appear shorter than mine. This is called length contraction. These are not illusions. They are not optical tricks. They are real, measurable physical effects. Time genuinely passes slower for you relative to me when you are moving at high speed relative to me. And this has been confirmed by countless experiments. Atomic clocks flown on airplanes tick slightly slower than identical clocks left on the ground, exactly as Einstein's equations predict. Muons, subatomic particles created in the upper atmosphere, should decay long before reaching the ground at the speed they travel. But because time is dilated from our perspective, they survive long enough to be detected at the surface. Special relativity is not speculation. It is one of the most thoroughly tested theories in all of physics. But here is what matters for our story. The consequences of special relativity reveal something profound about the nature of space and time. They are not independent, they are intertwined. What I measure as purely spatial distance, you might measure as a combination of spatial distance and time interval, depending on our relative motion. Space and time are mixed together by relative motion. They are not separate entities. They are aspects of a single entity. This insight was crystallized in 1908 by a mathematician named Hermann Minkowski, who had actually been one of Einstein's teachers. Minkowski gave a famous lecture in which he declared, "And I find these words incredibly powerful, henceforth space by itself, and time by itself, are doomed to fade away into mere shadows. And only a kind of union of the two will preserve an independent reality. That union is what we now call space-time. 4-dimensional space-time. 3 dimensions of space and 1 dimension of time woven together into a single 4-dimensional fabric." Minkowski showed that the natural mathematical framework for special relativity is a 4-dimensional space where events are specified by 4 coordinates. 3 spatial coordinates, x, y, and z, plus 1 time coordinate, t. The distance between 2 events in spacetime is not measured by the usual spatial distance formula. Instead, it is measured by something called the spacetime interval, which looks like this. You take the spatial distance squared and subtract the time component squared times the speed of light squared. That minus sign is crucial. It is what makes time fundamentally different from space. In a purely spatial 4-dimensional space, all 4 terms would have the same sign. But in spacetime, time gets a minus sign. This is called the Minkowski metric, and it defines the geometry of flat spacetime. This was a paradigm shift. For the first time in the history of physics, space and time were united into a single entity. Spacetime, and the geometry of this entity, was not just a mathematical convenience. It was physics. The behavior of objects in special relativity could be understood as the geometry of paths through 4-dimensional spacetime. But Einstein was not done. Special relativity dealt with objects moving at constant velocities. What about gravity? What about acceleration? Einstein spent the next 10 years, from 1905 to 1915, working on this problem. The result was his general theory of relativity, which I consider to be the single most beautiful intellectual achievement in human history. The central idea of general relativity is breathtaking in its elegance. Gravity is not a force. Let me repeat that. Gravity is not a force. In Newton's picture, gravity was a mysterious force that reached across empty space and pulled objects toward each other. The Earth pulls the moon. The sun pulls the Earth. But Newton himself was deeply uncomfortable with this idea. How does the Earth know the moon is there? How does the gravitational force travel instantaneously across the void? Newton called this action at a distance and famously said he framed no hypotheses about how it worked. Einstein's answer was revolutionary. Gravity is not a force acting through space. Gravity is the curvature of space-time itself. Massive objects like the sun do not reach out and pull other objects toward them. Instead, they curve the space-time around them. And objects moving through curved space-time follow the natural paths dictated by that curvature. The Earth does not orbit the Sun because the Sun is pulling it. The Earth orbits the Sun because the Sun has curved space-time around it, and the Earth is following the straightest possible path through that curved space-time. In flat space-time, the straightest path is a straight line. In curved space-time, the straightest path can be a curve, an orbit. Think of it like this. Imagine placing a heavy bowling ball in the center of a stretched rubber sheet. The ball creates a dip in the sheet. Now roll a marble across the sheet. If you roll it in a straight line far from the bowling ball, it will travel in a roughly straight path. But if you roll it near the bowling ball, it will curve toward the dip. Not because the bowling ball is pulling the marble with some invisible force, but because the marble is following the curved surface of the sheet. That is gravity, according to Einstein. Not a force, but geometry. The geometry of space-time. Einstein encoded this idea in his field equations of general relativity. These equations relate the curvature of four-dimensional space-time to the distribution of matter and energy within it. In simple terms, matter tells space-time how to curve, and curved space-time tells matter how to move. The equations are written using the mathematical language of differential geometry, tensors, and Riemannian manifolds. They are technically challenging, but conceptually, they say something beautifully simple. The geometry of space-time is not fixed and absolute, as Newton thought. It is dynamic. It responds to the presence of matter and energy, and the response of space-time's geometry is what we experience as gravity. General relativity has been confirmed by a staggering number of experiments and observations. It predicted that light would be bent by gravity. Confirmed, during the solar eclipse of 1919, Arthur Eddington observed that light from distant stars was bent by the sun's gravity by exactly the amount Einstein predicted. General relativity predicted that clocks in stronger gravitational fields would tick slower. Confirmed, GPS satellites must correct for this effect, or they would accumulate errors of about 10 kilometers per day. General relativity predicted that massive objects should emit gravitational waves, ripples in the fabric of spacetime. Confirmed, in 2015, the LIGO experiment directly detected gravitational waves from the collision of two black holes a billion light-years away. Exactly matching Einstein's predictions, general relativity predicted the existence of black holes, regions where spacetime is so extremely curved that nothing, not even light, can escape. We have now directly imaged the shadows of black holes with the Event Horizon Telescope. Einstein's theory works. It is not speculation. It is the most precisely tested theory of gravity ever constructed. And here is the lesson from Einstein that is absolutely critical for our story about extra dimensions. Einstein showed that the geometry of spacetime is physics. The shape, the curvature, the structure of spacetime itself determines how objects move, how light bends, how time flows. If you change the geometry, you change the physics. This idea that physical forces can be understood as geometric properties of spacetime is the conceptual foundation on which everything else we are going to discuss is built. Because once you accept that gravity is geometry, a natural question arises. What if there are more dimensions of spacetime than we can see? What if the geometry of those hidden dimensions explains not just gravity, but all the other forces of nature too? Einstein himself spent the last 30 years of his life trying to unify gravity with electromagnetism. He wanted to show that both forces could be understood as aspects of a single geometric framework. He failed, but the reason he failed may have been that he was working in 4 dimensions, and 4 dimensions are simply not enough. This brings us to one of the most underrated stories in the history of physics. The story of Theodore Kaluza and the fifth dimension. In 1919, a relatively unknown German mathematician named Theodore Kaluza was sitting at his desk, working through the mathematics of Einstein's general relativity. And he did something extraordinarily simple, yet extraordinarily bold. He asked a question that nobody else had thought to ask. What if space-time has 5 dimensions instead of 4? What if, alongside the 3 dimensions of space and 1 dimension of time that we know about, there is 1 additional spatial dimension that we somehow cannot see? Kaluza wrote down Einstein's field equations, the equations of general relativity, but in 5 dimensions instead of 4. And when he worked out the mathematics, something astonishing happened. The 5-dimensional equations naturally split into 3 parts. The first part was identical to Einstein's 4-dimensional equations of gravity. That was expected. If you write down gravity in 5 dimensions, you should get gravity in 4 dimensions as a subset. But the second part was completely unexpected. The second part of the 5-dimensional equations was identical to Maxwell's equations of electromagnetism. Electromagnetism, the force that governs light, electricity, magnetism, chemistry, and biology, popped out of the geometry of a 5th dimension as naturally as gravity pops out of the geometry of 4-dimensional space-time. And there was a third part, a scalar field that we will come back to later. But the key result was stunning. Gravity plus electromagnetism equals the geometry of 5-dimensional space-time. Let me explain why this is so remarkable. In 4-dimensional space-time, the geometry is described by something called the metric tensor. You can think of the metric tensor as a mathematical object that tells you the distance between any 2 nearby points in space-time. In 4 dimensions, the metric tensor is a 4x4 symmetric matrix, which means it has 10 independent components. These 10 components describe gravity. They encode all the information about the curvature of space-time. In 5 dimensions, the metric tensor is a 5x5 symmetric matrix with 15 independent components. Now here is the magic. Of those 15 components, 10 describe gravity in the usual 4-dimensional way. 4 of them, the components mixing the 5th dimension with the 4 usual dimensions, turn out to describe electromagnetism. And the remaining 1 component describes a scalar field called the dilaton. So the extra 5 components that come from adding just 1 more dimension to space-time automatically contain electromagnetism. Nobody put electromagnetism in. Nobody designed the theory to produce Maxwell's equations. It just emerged naturally from the geometry of a 5-dimensional space. This is not a trick or a coincidence. It is a deep mathematical truth about the structure of higher dimensional geometry. The gauge symmetry of electromagnetism, the mathematical structure that makes Maxwell's equations work the way they do, is precisely the symmetry of rotations in the 5th dimension. Electric charge, in Kaluza's theory, is literally momentum in the 5th dimension. Just as ordinary momentum is motion in one of the 3 spatial directions, electric charge is motion in the 5th spatial direction. This is profound. One of the deepest properties of electromagnetism, the fact that electric charge exists, is reinterpreted as a simple geometric property of a hidden dimension. Kaluza wrote up his results and sent the paper to Einstein. Einstein was stunned. He was so struck by the result that he sat on Kaluza's paper for 2 years before finally helping him publish it in 1921. In a letter to Kaluza, Einstein wrote that the idea of achieving unification through a 5-dimensional cylinder world had never occurred to him and that he liked the idea very much. But there was an obvious problem with Kaluza's theory. If there is a fifth dimension, why can we not see it? Why do we not notice it in everyday life? Why has no experiment ever detected it? In 1926, a Swedish physicist named Oscar Klein proposed an answer. What if the fifth dimension is compactified? What if it is curled up into a tiny circle, so small that it is invisible to us? Here is the analogy that makes this clear. Imagine looking at a garden hose from a great distance. From far away, the hose looks like a one-dimensional line. It appears to have only length. But if you zoom in, you see that the hose actually has a circular cross-section at every point along its length. There is a tiny circle at every point. An ant crawling on the hose could move in two directions along the length of the hose and around the circular cross-section. The hose is actually two-dimensional, but from far away, one of those dimensions is invisible. Klein proposed that the fifth dimension is like the circular cross-section of the garden hose, but much, much smaller. At every point in our four-dimensional space-time, there is a tiny circle, a compactified fifth dimension, with a radius so small that we cannot detect it. Klein calculated how small the fifth dimension would need to be in order to be consistent with the observed properties of electromagnetism. The answer was the Planck length, roughly 10 to the minus 35 meters. To appreciate how small this is, consider that a proton has a radius of about 10 to the minus 15 meters. The Planck length is 20 orders of magnitude smaller than a proton. That is a factor of 100 billion. If a proton was scaled up to the size of the observable universe, the Planck length would be about the size of a grain of sand. At that scale, no experiment could ever directly observe the fifth dimension. But the idea gets even more beautiful. Because the fifth dimension is a circle, a closed loop, the momentum of a particle in the fifth dimension is quantized. This is the same principle that governs standing waves on a guitar string. A guitar string can only vibrate at certain frequencies because it is fixed at both endpoints. Similarly, a particle moving in a circular fifth dimension can only have certain values of momentum in that direction. And since momentum in the fifth dimension is electric charge, this means that electric charge must come in discrete units. It must be quantized. Part 2. This is a remarkable result. One of the deepest mysteries of electromagnetism, the fact that electric charge always comes in integer multiples of the elementary charge, the charge of an electron, gets a beautifully simple geometric explanation in Kaluza-Klein theory. Charge is quantized because the fifth dimension is a circle. So Kaluza-Klein theory achieved something extraordinary. It showed that gravity and electromagnetism, two seemingly different forces of nature, could be unified as aspects of a single geometric framework in 5 dimensions. It explained charge quantization as a consequence of the compactified geometry, and it established the template for all future attempts to use extra dimensions in physics. The basic idea that what we perceive as forces in 4 dimensions might actually be the geometry of hidden dimensions was born. But Kaluza-Klein theory was not the final answer. It had serious problems. First, it only unified gravity with electromagnetism. In the 20th century, physicists discovered 2 additional fundamental forces: the strong nuclear force, which holds atomic nuclei together, and the weak nuclear force, which is responsible for certain types of radioactive decay. Kaluza-Klein theory said nothing about these forces. Second, the scalar field, the dilaton, that the theory predicted had never been observed. Third, the theory was classical. It did not incorporate quantum mechanics, which governs the behavior of matter at the smallest scales. And fourth, it provided no explanation for why the fifth dimension should be compactified in the first place. Why is it curled up so small? What mechanism makes it that way? Despite these problems, the core insight of Kaluza-Klein theory, the idea that extra dimensions could unify the forces of nature, remained alive. It went into hibernation for several decades as physics pursued other directions. The middle of the 20th century was dominated by the development of quantum field theory and the standard model of particle physics. Physicists focused on understanding the quantum behavior of particles and forces, building the incredibly successful framework that describes three of the four fundamental forces: electromagnetism, the strong force, and the weak force. The standard model was completed in the 1970s and has been confirmed by virtually every experiment since. But the standard model has its own problems. It does not include gravity. It has about 20 free parameters, numbers that must be measured experimentally and plugged in by hand. It does not explain why there are 3 families of particles instead of 1 or 2 or 17. It does not explain why the masses of particles are what they are. It does not explain dark matter or dark energy. And it does not explain why gravity is so incredibly weak compared to the other forces. The standard model is a spectacular achievement, but it is clearly incomplete. And in the late 1960s and early 1970s, the idea that would eventually bring extra dimensions back into physics emerged from a completely unexpected direction. Not from gravity, not from cosmology, but from the strong nuclear force. In the summer of 1968, a young Italian physicist named Gabriele Veneziano was working at CERN, the European Particle Physics Laboratory in Geneva, Switzerland. He was trying to understand the strong nuclear force, the force that holds quarks together inside protons and neutrons. Physicists at the time were studying what happened when protons and other strongly interacting particles were smashed together at high energies. They observed complex patterns in the way particles scattered off each other, patterns that were difficult to explain with existing theories. Veneziano was looking at the mathematical properties these scattering patterns should have, and he made a remarkable observation. He found that an obscure mathematical function, the Euler beta function, originally studied by the great mathematician Leonhard Euler in the 18th century, perfectly described the scattering amplitudes of strongly interacting particles. The Euler beta function had exactly the right mathematical properties. It was crossing symmetric, meaning it looked the same regardless of which particles were incoming and which were outgoing, and it reproduced the patterns of resonances that experimentalists were observing. Veneziano's result was striking, but it raised an immediate question. The Euler beta function is a purely mathematical object. What physical system would produce scattering amplitudes described by this function? What underlying physics was the beta function telling us about? 2 years later, in 1970, 3 physicists working independently arrived at the same answer. Yoichiro Nambu in Chicago, Holger Beck-Nielsen in Copenhagen, and Leonard Susskind in New York all realized that the Euler beta function describes the quantum mechanics of a vibrating string. Not a string on a guitar or a violin, but a fundamental one-dimensional object with no thickness, extending through space. The scattering amplitudes that Veneziano had found were exactly the amplitudes produced by strings colliding, joining, and splitting apart. This was the birth of string theory. And it was an accident. Nobody set out to invent a theory of fundamental strings. The strings emerged from the mathematics. The Euler beta function led to strings. and strings led to a completely new picture of fundamental physics. But before we go deeper into string theory, let me pause and make sure you understand why this is so revolutionary. In the standard model of particle physics, the fundamental objects are point particles. An electron is a point, zero-dimensional. It has no size, no shape, no internal structure. It is a mathematical point. A quark is a point. A photon is a point. All fundamental particles in the standard model are points. This is the traditional picture of particle physics that has dominated for decades. String theory replaces this picture with something entirely different. In string theory, the fundamental objects are not points. They are strings. Tiny, one-dimensional objects that have length but no width or height. These strings are incredibly small, roughly the Planck length, about 10 to the minus 35 meters. At the distances we can probe with current experiments, strings are so tiny that they would appear to be points. But at the Planck scale, their one-dimensional nature would become apparent. And here is the key idea. These strings can vibrate. Just like a guitar string vibrates in different patterns to produce different musical notes, fundamental strings vibrate in different patterns to produce different particles. One vibration pattern produces an electron. A different vibration pattern produces a quark. Another produces a photon. Another produces a graviton. The hypothetical quantum of the gravitational field. All the different particles we observe in nature, all the quarks, leptons, bosons, and even the graviton, are just different vibration patterns of a single type of fundamental string. This is an incredibly powerful idea. Instead of having dozens of different fundamental particles, each with its own properties that must be specified by hand, you have one fundamental object, the string, and all the diversity of particles emerges from the different ways it can vibrate. It is as if all of music came from a single string on a single instrument, with every note, every harmony, every symphony arising from different vibration patterns of that one string. There are two basic types of strings. Open strings have two endpoints. They are like a piece of spaghetti, with a beginning and an end. Closed strings form a loop. They are like a rubber band, with no endpoints. Open strings give rise to gauge bosons, the particles that carry forces. The photon, for example, comes from an open string vibration. Closed strings give rise to a very special particle, the graviton. The graviton is the quantum of gravity, the particle that, in a quantum theory of gravity, would mediate the gravitational force the same way the photon mediates the electromagnetic force. The fact that closed string vibrations automatically include the graviton means that string theory automatically includes gravity. This is enormous. The standard model cannot incorporate gravity. Decades of effort to quantize gravity using the methods of quantum field theory have failed because of mathematical infinities that cannot be removed. But string theory includes gravity naturally, without being forced. The graviton just pops out of the mathematics as one of the vibration modes of a closed string. Now, the original version of string theory, developed in the early 1970s, was called bosonic string theory, and it had some serious problems. The most immediately obvious problem was that it only described bosons. In particle physics, there are two broad categories of particles. Bosons are force-carrying particles like the photon and the gluon. They have integer values of a quantum property called spin, 0, 1, 2, and so on. Fermions are matter particles like electrons and quarks. They have half-integer values of spin, 1/2, 3/2, and so on. The distinction between bosons and fermions is fundamental. Bosons obey one set of quantum statistics, and fermions obey another. The matter that makes up your body is made of fermions. The forces that hold your body together are carried by bosons. You need both to have a universe. But bosonic string theory could only describe bosons. It had no fermions, no electrons, no quarks, no matter. A universe described by bosonic string theory would be a universe of forces with nothing for those forces to act on. That is clearly not our universe. The second problem was even stranger. Bosonic string theory predicted the existence of a particle called a tachyon. A tachyon is a particle with a negative value of mass squared. In relativity, a particle with negative mass squared would travel faster than the speed of light. This is not just exotic, it is a sign of a deep instability in the theory. The tachyon signals that the vacuum state of the theory, its ground state, is unstable. It is like a ball balanced on top of a hill. Any tiny perturbation will cause it to roll down. A theory with a tachyon is a theory that is sitting at an unstable point and will inevitably decay to something else. And the third problem, the one most relevant to our story, was the number of dimensions. When physicists carefully worked through the mathematics of bosonic string theory, demanding that the theory be internally consistent, they found that it only worked in 26 dimensions. 25 dimensions of space and 1 dimension of time. In any other number of dimensions, the theory produced mathematical contradictions, ghost states with negative probabilities, violations of fundamental physical principles. The number 26 was not a choice. It was not a parameter you could adjust. It was fixed by the mathematics. We will see exactly how later. So bosonic string theory had no matter, an unstable vacuum, and required 26 dimensions. As a theory of our universe, it was clearly wrong. But the mathematical beauty of the framework, the way strings naturally included gravity, the elegant connection between vibration patterns and particle properties was too compelling to abandon. Physicists did not throw string theory away. Instead, they tried to fix it. The fix came from a concept called supersymmetry. In 1971, Pierre Ramond, working on his own, and shortly after André Neveu and John Schwartz, working together, found a way to include fermions in string theory. The key was to add a new type of symmetry to the theory, a symmetry that related bosons and fermions. This symmetry, called supersymmetry, pairs every boson with a corresponding fermion and vice versa. For every force-carrying particle, there is a corresponding matter particle, and for every matter particle, there is a corresponding force-carrying particle. In a supersymmetric theory, the electron would have a bosonic partner called the selectron. The quark would have a partner called the squark. The photon would have a partner called the photino. The graviton would have a partner called the gravitino. These partner particles are called superpartners. None of them have been observed experimentally, which is either because they are too heavy for current particle accelerators to produce, or because supersymmetry is not a feature of our universe at the energy scales we can access. But here is what happened when supersymmetry was added to string theory. First, the tachyon disappeared. The instability in the vacuum was removed. The theory became stable. Second, fermions were included naturally. Matter particles arose from the vibrations of the string, just as force-carrying particles did. Third, and this is the fact that brings us to the central topic of this video, the number of required dimensions dropped from 26 to 10. Let me say that again, because it is the most important fact in this video. When you add supersymmetry to string theory, The number of dimensions required for mathematical consistency drops from 26 to exactly 10. 9 dimensions of space and 1 dimension of time. The theory that includes supersymmetry is called superstring theory, and it is the version of string theory that physicists have been studying intensively since the 1970s. For many years, superstring theory was considered a fringe topic. Only a handful of physicists worked on it. The mainstream of particle physics was focused on quantum field theory and the Standard Model, which were producing spectacular experimental predictions and confirmations. String theory, with its extra dimensions and its lack of experimental predictions, seemed like a mathematical curiosity at best. That changed in the summer of 1984 in what is now known as the first superstring revolution. Two physicists, Michael Green from Queen Mary College in London and John Schwarz from Caltech, were working on a technical problem in superstring theory related to mathematical consistency. Specifically, they were checking whether superstring theory was free from anomalies. An anomaly, in the context of quantum field theory, is a situation where a symmetry that exists in the classical theory is broken by quantum effects. Anomalies are bad. Certain types of anomalies, called gauge anomalies, make a theory mathematically inconsistent. They lead to violations of conservation laws, negative probabilities, and other nonsensical results. If a theory has gauge anomalies, it is not just wrong, it is meaningless. The equations contradict themselves. Green and Schwarz discovered something remarkable. They showed that all potential anomalies in superstring theory cancel out. Every single one. The theory is completely free of gauge anomalies. But, and this is the crucial point, the anomaly cancellation only works in exactly 10 spacetime dimensions and only for 2 specific choices of the gauge symmetry group, SO and E8 times E8. In any other number of dimensions or with any other gauge group, the anomalies do not cancel, and the theory is inconsistent. This result sent shockwaves through the theoretical physics community. Here was a theory that naturally included gravity, that was free of the mathematical infinities that plagued quantum gravity, and that was mathematically consistent in a way that fixed the number of space-time dimensions and the gauge group. Within months, hundreds of physicists switched their research to string theory. The first superstring revolution had begun. By the late 1980s, physicists had mapped out the landscape of superstring theories and found something surprising. There were 5 of them. 5 different superstring theories, all mathematically consistent, all requiring exactly 10 dimensions, but differing in their specific properties. Let me describe each one briefly. Type 1 superstring theory contains both open and closed strings. The open strings carry gauge charges associated with the symmetry group SO. This theory is special because it includes unoriented strings, meaning you cannot tell which direction along the string is which. Type Ia superstring theory contains only closed strings. It is non-chiral, meaning it treats left-handed and right-handed vibrations symmetrically. It includes D branes of even dimension, which we will discuss later. Type Ib superstring theory also contains only closed strings. But unlike type Ia, it is chiral, meaning left-handed and right-handed vibrations are treated differently. It includes D branes of odd dimension. Heterotic SO superstring theory is a closed string theory with a remarkable construction. The left-moving vibrations of the string live in 26 dimensions, like bosonic string theory, while the right-moving vibrations live in 10 dimensions, like superstring theory. This sounds like it should not work, but it does. The extra 16 dimensions on the left-moving side are compactified on a specific torus that produces the gauge group SO. Heterotic E8 times E8 superstring theory has the same heterotic construction, but the 16 extra left moving dimensions are compactified differently, producing the gauge group E8 times E8. This particular version was considered especially promising for describing our universe because the E8 times E8 gauge group contains the gauge groups of the standard model as subgroups. 5 theories, all in 10 dimensions, all mathematically consistent, all claiming to be the theory of everything. But 5 theories of everything? That is 4 too many. If string theory is supposed to be the unique, fundamental description of reality, why are there 5 versions? This was a deeply troubling question, and it hung over the field for nearly a decade. We will come back to how it was resolved later, with M-theory and the second superstring revolution. But first, we have arrived at the question that this entire video is about. We have built all the foundations. We understand what dimensions are. We understand how Einstein unified space and time. We understand how Kaluza and Klein showed that extra dimensions can unify forces. We understand what string theory is and how it works. Now it is time to answer the central question. Why exactly 10 dimensions? Where does the number 10 come from? Why does the math demand it? This is the deepest and most technical part of the video, but I am going to walk you through it step by step as clearly as I can. Because the answer to this question is not just a technical detail. It is one of the most remarkable results in the history of theoretical physics. It shows that a theory can predict the number of dimensions of spacetime, something that no other physical theory has ever done. To understand where the number 10 comes from, we first need to understand a concept called the worldsheet. When a point particle moves through spacetime, it traces out a path. We call this path the world line of the particle. It is a one-dimensional curve in spacetime. At each moment in time, the particle is at a point, and the collection of all those points over time forms a line. Now, a string is not a point. It is a one-dimensional object extended in space. When a one-dimensional string moves through time, it sweeps out a two-dimensional surface. We call this surface the worldsheet. If the string is open, with 2 endpoints, the worldsheet looks like a ribbon or a strip. If the string is closed, forming a loop, the worldsheet looks like a tube or a cylinder. The worldsheet is absolutely central to string theory. In fact, you can think of string theory as a theory that lives on the worldsheet. The physics of the string is described by a two-dimensional quantum field theory defined on this two-dimensional worldsheet surface. The fields in this two-dimensional theory are the coordinates of the string in spacetime. If spacetime has d dimensions, then there are d fields on the worldsheet, which we can call x0, x1, x2, all the way up to xd-1. Each field tells you the position of the string in one spacetime dimension. As you move around on the worldsheet, these fields vary, describing how the string moves and vibrates in spacetime. This is a beautiful reformulation. Instead of thinking about strings wiggling in 10-dimensional spacetime, you can think about a two-dimensional quantum field theory on the worldsheet. The question of how many spacetime dimensions are consistent then becomes a question about the mathematical consistency of this two-dimensional theory. And that is where the number 10 will come from. The worldsheet theory has a crucial symmetry that it must possess. This symmetry is called conformal symmetry. To understand what conformal symmetry means, imagine drawing a picture on a rubber sheet. Now stretch the rubber in some direction, or compress it, or deform it in some complicated way, but always preserving the angles between lines. The shapes of objects might change. A circle might become an ellipse. A square might become a parallelogram. But the angles at which lines meet are preserved. A transformation that preserves angles is called a conformal transformation, and a theory that is unchanged by such transformations has conformal symmetry. Why does the worldsheet theory need conformal symmetry? Because the specific coordinates we use on the worldsheet are arbitrary. The worldsheet is just a surface, and we can parameterize it with any coordinate system we like. Just as the physics of spacetime should not depend on whether we use Cartesian or polar or spherical coordinates, the physics on the worldsheet should not depend on the specific coordinate system we use on the worldsheet surface. This gauge freedom, the freedom to choose coordinates, leads to the requirement that the worldsheet theory be conformally invariant. If it is not, then different choices of worldsheet coordinates would give different physical predictions, which would mean the theory is ill-defined. Now, here is the crux. In classical physics, conformal symmetry is easy to maintain. You can write down a conformally invariant classical theory on the worldsheet for any number of space-time dimensions d. The classical worldsheet theory works perfectly well in 4 dimensions, 10 dimensions, 100 dimensions, or any other number. There is no constraint on d at the classical level. But we do not live in a classical universe. We live in a quantum universe. And when you quantize a classical theory, turning it into a quantum theory, symmetries can be broken. A symmetry that exists in the classical theory can fail to survive the transition to the quantum theory. When this happens, we say the symmetry has an anomaly. The quantum effects that are absent in classical physics can conspire to violate the symmetry. When conformal symmetry is broken by quantum effects on the worldsheet, the result is called the conformal anomaly, or sometimes the Weyl anomaly. And when the conformal anomaly is present, disaster strikes. The theory develops ghost states, states with negative probability. Unitarity, the requirement that probabilities add up to 1, is violated. The theory becomes mathematically meaningless. Physical predictions become nonsensical. A theory with an unresolved conformal anomaly is not merely wrong, it is not even a coherent theory. It cannot make any predictions at all, because the mathematical framework it is built on collapses. Therefore, the conformal anomaly must be cancelled. The quantum worldsheet theory must be exactly conformally invariant. And it is this requirement, the requirement of conformal anomaly cancellation, that fixes the number of space-time dimensions. Let me walk you through the mathematics of how this works. I will keep it as clear as possible while being faithful to the actual physics. In a conformal field theory, there is a quantity called the central charge, usually denoted by the letter C. The central charge is a number that characterizes the theory. It appears in the algebra of conformal symmetry generators, called the Virasoro algebra. Specifically, it appears in the commutation relations of the Virasoro generators as an extra term, a central extension that vanishes classically but is present quantum mechanically. The central charge tells you, roughly speaking, how many degrees of freedom the theory has. Now, each field on the worldsheet contributes to the central charge. A single bosonic field, like one of the spacetime coordinate fields x, contributes a central charge of 1. So if spacetime has d dimensions, the d coordinate fields contribute a total central charge of d to the worldsheet theory. But the worldsheet theory is not just the coordinate fields. When we quantize the theory, we must also deal with the gauge symmetry of the worldsheet, the freedom to choose coordinates. To handle this properly in the quantum theory, we introduce auxiliary fields called ghost fields. These ghost fields are mathematical tools, not physical particles. They are needed to properly account for the gauge symmetry in the quantum theory, a procedure called gauge fixing. The ghost fields also contribute to the central charge, but with a negative sign. For bosonic string theory, the ghost fields contribute a central charge of -26. This is a specific, calculable number that comes from the structure of the conformal gauge fixing procedure for the bosonic string. Now, for the conformal anomaly to cancel, the total central charge must be 0. This is the condition for the quantum worldsheet theory to be conformally invariant. If the total central charge is not 0, the theory has a conformal anomaly, and it is inconsistent. So we write, total central charge equals matter central charge plus ghost central charge equals 0. The matter central charge is just d, the number of space-time dimensions, since each dimension contributes 1. The ghost central charge is -26. Setting the total to 0, we get d minus 26 equals 0. Therefore, d equals 26. And that is why bosonic string theory requires 26 dimensions. It is not an arbitrary choice. It is not an aesthetic preference. It is the unique number of dimensions for which the quantum worldsheet theory is mathematically consistent. In any other number of dimensions, the conformal anomaly does not cancel, ghost states appear, probabilities become negative, and the theory is meaningless. Now let us do the same calculation for superstring theory, which is the version we actually care about. When we add supersymmetry to the worldsheet theory, each spacetime dimension contributes not just a bosonic coordinate field X, but also a fermionic partner field, usually denoted by the Greek letter psi. The bosonic field X contributes a central charge of 1, as before. The fermionic field psi contributes a central charge of 1/2. So each spacetime dimension contributes a total of 1 plus 1/2 equals 3/2 to the matter central charge. The ghost sector also changes. In addition to the bosonic ghosts from gauge fixing the worldsheet metric, we now have fermionic ghosts from gauge fixing the worldsheet supersymmetry. The bosonic ghosts still contribute -26 to the central charge. The fermionic ghosts, which are called superconformal ghosts, contribute +11. So the total ghost central charge is -26 plus 11 equals -15. Now apply the anomaly cancellation condition again. Total central charge equals 0. The matter central charge is d times 3/2. The ghost central charge is -15. So we get d times 3/2 minus 15 equals 0. Solving for d, we get d times 3/2 equals 15. Therefore d equals 10. 10, not 9. Not 11. Not 26. Exactly 10. This is the critical dimension of superstring theory. It is the unique number of space-time dimensions in which the quantum worldsheet theory of the superstring is conformally invariant and therefore mathematically consistent. Let me emphasize what just happened. We started with the simple assumption that fundamental objects are one-dimensional strings. We required that the theory be quantum mechanical. We required that it have supersymmetry. And we required that it be conformally invariant on the worldsheet, which is necessary for the theory to be well-defined and make consistent physical predictions. From these assumptions alone, the number of spacetime dimensions is fixed. We did not choose 10 dimensions. We did not put it in as an assumption. The theory predicted it. The number 10 emerged from the mathematics as the unique, consistent possibility. But let me show you that this result is not dependent on one particular way of doing the calculation. There is a completely independent derivation of d equals 10 that comes from a different approach called light cone quantization. This approach is more physical and gives additional insight into why the number of dimensions matters. In the light cone approach, you choose a specific coordinate system that simplifies the calculations. You pick one spatial direction and one time direction and form special combinations called light cone coordinates. In this gauge, the physical degrees of freedom of the string are the vibrations in the directions transverse to the string and perpendicular to its direction of motion. If spacetime has d dimensions, there are d-2 transverse directions. The -2 comes from subtracting 1 for time and 1 for the longitudinal direction along the string. Each transverse direction gives the string one set of oscillation modes. These are like the harmonics of a guitar string: the fundamental frequency, the second harmonic, the third harmonic, and so on. In the quantum theory, each of these modes is a quantum harmonic oscillator with discrete energy levels. Now, the ground state of these oscillators has a certain energy, called the zero-point energy. When you add up the zero-point energies of all the oscillation modes in all the transverse directions, you get the ground state energy of the string. This ground state energy determines the mass of the lightest particle in the theory. For the bosonic string, the ground state energy works out to be negative, which means the lightest particle has negative mass squared. The tachyon. For the superstring, the supersymmetry between bosonic and fermionic oscillators changes the calculation, and the ground state energy can be zero, giving a massless particle. But here is the key point. For the theory to be consistent, the ground state energy must have a very specific value. It must be such that the spectrum of particles includes a massless spin 2 particle, the graviton, with the correct properties. Specifically, a massless spin 2 particle in d dimensions must have exactly d-2 polarization states. It is a fundamental result in quantum field theory that a massless particle of spin s in d spacetime dimensions has a specific number of physical polarization states, and this number depends on d. When you calculate the number of states in the ground state of the superstring using the light cone approach, and you demand that the massless spin 2 state, the graviton, has the correct number of polarizations, you get the condition d-2 equals 8. Therefore, d equals 10. The same answer. 10. From a completely different approach. In the conformal anomaly approach, 10 came from requiring the total central charge to vanish. In the light cone approach, 10 comes from requiring the correct polarization states for the graviton. These are mathematically different derivations that arrive at the same result, which is strong evidence that d equals 10 is a deep and robust feature of the theory, not an artifact of a particular calculational technique. But wait, there is yet another way to see d equals 10. This third approach comes from Lorentz invariance, the symmetry that Einstein's special relativity demands. Lorentz invariance says that the laws of physics should look the same to all observers moving at constant velocity relative to each other. No direction in spacetime is special. The equations treat all spatial directions equally. In the light cone quantization approach, you break Lorentz invariance by choosing a special direction. This is fine as long as the physical predictions of the theory do not actually depend on which direction you chose. The theory must still be secretly Lorentz invariant, even though you have chosen a particular frame to do the calculation. You can check this by computing the commutation relations of the Lorentz group generators in the quantized theory. The Lorentz group is the mathematical group of rotations and boosts in spacetime, and its generators must satisfy specific algebraic relations for Lorentz symmetry to hold. When you do this calculation for the quantized superstring, you find that the commutation relations of the Lorentz generators are satisfied if and only if d equals 10. In any other number of dimensions, the Lorentz algebra is violated. The theory would treat different directions differently, distinguishing between the direction you chose for light cone quantization and the other directions. This would be a fundamental inconsistency, because the choice of direction was supposed to be arbitrary. So we have three independent arguments for d equals 10. Conformal anomaly cancellation on the worldsheet, correct polarization counting in the light cone gauge, and Lorentz invariance of the quantized theory. Three completely different mathematical requirements, coming from different aspects of the theory's consistency, all pointing to the same unique answer, 10 dimensions. This convergence of independent arguments is remarkable. It tells us that d equals 10 is not a quirk of one particular calculation or one particular assumption. It is deeply woven into the mathematical fabric of the theory. It comes from the fundamental requirements of quantum mechanics, special relativity, and the one-dimensional nature of strings. You cannot avoid it. You cannot adjust it. You cannot negotiate with it. The math says 10, and that is that. Now I want you to pause and appreciate the significance of what we have just seen. In every other physical theory, before string theory, the number of space-time dimensions is an input. In Newtonian mechanics, you say there are 3 dimensions of space, and then you write down the laws. If you wanted to do Newtonian mechanics in 5 dimensions, you could. The equations work fine. In general relativity, the Einstein field equations work in any number of dimensions. You can study 3-dimensional gravity, 4-dimensional gravity, 11-dimensional gravity. The equations do not care. In quantum field theory, you can define quantum field theories in 2, 3, 4, or any number of dimensions. The number of dimensions is something you choose. String theory is the first theoretical framework in the history of physics that predicts its own space-time dimensionality. The number of dimensions is not an input, it is an output. It is a prediction of the theory. And the prediction is 10. Whether this is a deep clue about the nature of reality or an indication that string theory is on the wrong track is a matter of ongoing debate. But the mathematical fact is undeniable. Within the framework of superstring theory, 10 is the only consistent number of space-time dimensions. No more, no less. If you have been following along carefully, you might ask, but what happens if d is not 10? What exactly goes wrong? Let me tell you, because understanding what goes wrong is just as illuminating as understanding what goes right. If d is less than 10, there are not enough degrees of freedom. The matter fields on the worldsheet do not contribute enough central charge to cancel the ghost contribution. The total central charge is negative. This means the theory contains states with negative norm, ghost states where the probability of finding the system in that state is negative. Negative probability is not just unusual, it is meaningless. Probability is by definition a number between 0 and 1. A negative probability means the mathematical framework has broken down completely. You cannot extract any physical predictions from such a theory because the basic rules of quantum mechanics, which require probabilities to be non-negative and to sum to 1, are violated. If d is greater than 10, there are too many degrees of freedom. The matter fields over-contribute to the central charge. The total central charge is positive. This leads to a different kind of problem. Lorentz invariance is broken. The theory treats the transverse directions differently from each other in a way that depends on the number of extra dimensions. Physical predictions would depend on arbitrary choices, like which direction you used for the light cone gauge. The theory becomes inconsistent in a different way. It gives different answers depending on how you set up the calculation, which means it is not really making well-defined predictions at all. Only at d equals 10 does everything work. The central charge vanishes. Ghost states are absent. Probabilities are positive. Lorentz invariance is preserved. The graviton has the correct properties. The theory is internally consistent. I sometimes think of it like a lock and key. The equations of string theory are like a lock with an incredibly complex mechanism. And the key that opens that lock, the key that makes the mechanism click into place, is the number 10. If you try to insert the number 9, it does not fit. The tumblers do not align. The lock jams. If you try 11, same problem. Only 10 makes everything click. Now, if you have been paying very close attention, you might have noticed something. I said that superstring theory requires 10 dimensions, but earlier I mentioned that there are 5 different superstring theories. How can there be 5 if the number of dimensions uniquely fixes the theory? The answer is that the number of dimensions is not the only thing that determines the theory. The detailed structure of the worldsheet theory, the types of strings, the gauge group, and other features differ between the 5 theories. They all share the requirement of 10 dimensions, but they differ in other aspects. It is like saying there are 5 different kinds of locks, but they all require the same key. The key is 10 dimensions, but the locks have different internal structures. Now let me pause here, because you have just absorbed the most technically demanding part of this entire video. The derivation of d equals 10 from conformal anomaly cancellation from light cone consistency, and from Lorentz invariance. If you followed all of that, you understand more about string theory than the vast majority of people on this planet. And if some parts were confusing, that is completely fine. The essential takeaway is this: the number 10 is not arbitrary. It is determined by the requirements of quantum mechanics, special relativity, and the consistency of the worldsheet theory. It is a mathematical necessity, not a choice. And that is what makes it so fascinating. If this is blowing your mind, take a second right now and hit that like button. I know that sounds like a small thing, but it really does make a difference. When you like this video, the algorithm shows it to more people who are curious about these deep questions. And drop a comment telling me which part amazed you the most. I read every single comment, and the discussions in the comment section of videos like this are often just as fascinating as the video itself. Now, let us move on to the next big question. String theory predicts 10 dimensions. We experience 4. Where are the other 6? This is where the story gets even more interesting. Remember Kaluza-Klein theory from earlier in this video? Kaluza showed that a 5th dimension could explain electromagnetism, and Klein showed that if the 5th dimension were curled up into a tiny circle, it would be invisible to us. String theory uses the same basic idea, but scaled up. Instead of one extra dimension curled into a circle, string theory has 6 extra dimensions curled into a much more complex shape. At every point in our 4-dimensional spacetime, at every location in space, and at every moment in time, there is a tiny 6-dimensional shape attached. These extra dimensions are so small, roughly at the Planck scale of 10 to the minus 35 meters, that we cannot detect them directly. They are compactified, curled up into a geometrical structure of extraordinary complexity. But these 6 extra dimensions cannot be just any shape. The shape must satisfy very specific mathematical requirements imposed by the consistency of the theory. Specifically, the 6-dimensional shape must preserve some supersymmetry in the remaining 4 dimensions. It must be Ricci flat, meaning that the average curvature vanishes, so that the equations of motion are satisfied. And it must have a very particular geometric structure called a Kala structure, which involves a specific relationship between the metric, the complex structure, and a mathematical object called the symplectic form. A 6-dimensional space that satisfies all of these requirements is called a Calabi-Yau manifold. This name comes from 2 mathematicians. Eugenio Calabi, an Italian-American mathematician, conjectured in 1954 that such spaces should exist. And Xing-Tung Yao, a Chinese-American mathematician, proved Calabi's conjecture in 1977 in a mathematical tour de force that earned him the Fields Medal, the highest honor in mathematics. The fact that these manifolds exist, that there are shapes satisfying all the required mathematical properties, is itself a remarkable mathematical result. What does a Calabi-Yau manifold look like? This is a question that does not have a simple answer, because we cannot truly visualize 6-dimensional shapes. Our visual system operates in 3 dimensions, and projecting a 6-dimensional shape into 3 dimensions inevitably loses enormous amounts of information. But mathematicians and physicists have created beautiful computer-generated images that represent 2-dimensional cross-sections or projections of Calabi-Yau manifolds. These images show incredibly intricate, multi-lobed shapes, like abstract sculptures or alien flowers. They have a fractal-like complexity that reflects the rich mathematical structure of the underlying 6-dimensional geometry.